Hi, everybody. Can you hear me?
Yes.
Thank you. We'll get started in about a minute or so. All right, it's 10 a.m. We'll get started here. So what I'm going to do is I'm going to share my screen here, and I'll make sure that everybody can see that I'm sharing it. Okay, desktop. All right, can you see my screen?
Yes.
Thank you. Appreciate that. All right. Let's get out of here. So what I wanted to do today was, at least at the first part, I wanted to focus on the stuff that I had said that you need to look at for today's Zoom meeting, which was to do with these questions, question 3 and question 4 on the paper tests. And then I'll go through the similar questions that are on the ungraded copy of test 1. All right, so just to give you a bit of context as to what we're doing, somebody's got something going. If you wouldn't mind muting, please. I hear some music in the background.
Oh, geez. Yeah, I'm sorry about that. It's my roommate.
That's okay. Thank you. Appreciate it. All right, so we've got the first part here, which is to figure out the reaction quotient, which will allow us to determine which way the reaction is actually going. The K there is what's going on at equilibrium. And in order to figure this out, we're using the equilibrium expression. And we've got Q, which equals products over reactants. And it's going to be all of the products multiplied together over all of the reactants multiplied together. So you see, by multiplying together, I mean C2C becomes C squared, or C times C. Likewise, A3A becomes A cubed, or A times A times A, and then that's multiplied by B squared as well. Then in order to get that Q value, which comes out to be 0.00531, and it's optional to include the units on big K. So sometimes we do, sometimes we don't. This student happened to. We don't need to include it. And what we get there is a Q value that results from the subbing in of the values we have for those concentrations. And you can see that presently, if we have those concentrations of A, B, and C, we're not at equilibrium because Q doesn't equal K. We know what K equals because we're told it's 0.20, but it actually turns out it's 0.00531. So that's the first part of the question, is just to determine whether or not it is at equilibrium. And there's many times it could be, as long as that combination of concentrations multiplied out to give 0.2, then 0.20, then it would be at equilibrium. Anybody have any questions about A so far? All right, let's look at B. And it says, if the reaction is not at equilibrium, which way will the reaction shift and why? Well, we know which way it's going to shift because we know what Q is and we know what K is. And what we can see from this one is that Q is less than K. And that's what we know so far. And we get that just by comparing the two values. It's clear that the Q is less than 0.20. So what that means is we have to ask ourselves a question. The premise we're working on here is that a reaction that's not at equilibrium will want to be at equilibrium, and it will do whatever it can in order to get to that point. So looking at the actual reaction itself and the way that we set up Q here, we know that Q is smaller than K, so we know Q has to get bigger. Now, if Q is going to get bigger, the only way that happens is if C gets bigger or A and B get smaller. Now, it turns out that if C is getting bigger, then A and B must be getting smaller because it's A and B that are being used to make C. So we know that the reaction is going towards the product side. Okay, I'll stop here for a second at B. Does anybody have any questions about how I know the reaction is shifting towards the product side?
This isn't specifically to that, but I noticed in the lab manual that it would talk about left or right versus products and reactants, but it almost seemed opposite according to how we write the equations. I didn't understand the directions.
Well, I suppose left is always reactants and right is always products, you know, as the reaction's written. That's really all I can. It should be consistent with products and reactants, with left meaning reactants and products meaning right meaning products.
Okay, I do see where it does say shifts left, but then reduces excess product. So it says the word product, but it's talking about the reactants, and then
yeah, that can be a bit confusing the way that's set up. But
okay.
just to think of left as being reactants and right as being products, I think would be fine.
Okay.
You'll see both. Sometimes people are more comfortable with directions rather than specifically talking about reactants or products.
Okay.
Let's see. The next part, C, what we're doing is it's important to note the first part of that question. It says, consider the above reaction at equilibrium. So now we're not talking about situation in A and B anymore. We're actually talking about the reaction at equilibrium, which means that anything we do to it is going to create a disturbance in that reaction. And the reaction will be taken out of equilibrium by doing any of these four things, or at least possibly doing any of these four things. Then we can end up being out of equilibrium, in which case the reaction is going to want to get back to equilibrium. So once we've placed this stress on the reaction, we have to determine, well, which way is the reaction going to go in order to compensate for that stress? In other words, what's going to happen to the reaction to make it get back to K? Because what we're doing is clearly removing it from being at K, and now we have to get back there. So if we've got a situation here where we're removing A, so I would bring your focus, we'll write out the K expression here since we are at K. But the K expression is going to actually be the same as the Q expression. The difference being, of course, that the K expression only applies when the reaction's at equilibrium. And then once we apply this stress, we're really just looking at the Q process anyway, just like we were before. So if we're removing A, that means that this is going to get less. And if that's getting less, what that means is that Q will end up being greater than K. So I'll stop there for a second. I want to make sure that people understand that removing A, which means making that less, will make Q greater than K. Does anybody have any questions about that?
All right, so my question is, so whenever we're dealing with Q, that's the initial, and then K is equilibrium, right?
Well, in this case, we're actually starting at equilibrium, and then by removing A, we take it out of equilibrium, and we can figure out what Q is relative to what K was.
Okay. All right.
Is that fair enough? You have to start at K though.
Wait. Okay. Okay. So we start at equilibrium, which is K, and then we gotta figure out what A is.
Well,
and that's Q.
Well, we're removing A.
Yeah.
And that means that the bottom of the equation there is going to get smaller, which makes Q larger than what K was.
So if it gets larger, then it's going to shift over to the reactant side.
Yes.
Yeah. So, but if our products are bigger, then it's going to stay to the product side. Like it's going to lean right.
Well, you mean if we added C or remove C?
We're talking about question 3, right?
We're talking about question 3, part C, part 1. This one here. I'm looking at this one here.
Okay. Sorry, I was unprepared.
I'm sorry. Does it matter which reactant you move? I mean, you said A. Was there reasoning for A versus B?
Only because it said removing A here.
Okay. Okay.
But removing B would have the same effect.
Okay. If it asked you what is one thing that you could do.
No, I'm not going to ask you that.
Okay.
No, it's just going to ask you the effect of doing something.
Okay.
And it's very specific about what it's asking you to do.
Okay.
But you're right. Either A or B could do that. We could talk about those kinds of questions, but those aren't the kind of questions you're going to be asked.
Okay.
Here.
Okay. No problem.
So Adam, what I'm saying here is, if this said removing C, then what would happen is that Q would end up being smaller relative to K, which would mean the reaction would have to move towards the product side if we removed C.
If we remove C.
Yeah.
Well, I mean, like, but I don't know. I'm thinking like the same way as like, if A and B are still getting bigger, and if we remove C, A and B are still going to be as big. So wouldn't it still go to the reactant side? Or am I just overthinking it?
If we remove C, now think of it. No, think of it this way. If you're removing C from the reaction, what's the reaction going to want to do? Isn't it going to want to replace the C that you removed?
Yeah.
Right. So it'll move to that side.
Okay.
Likewise, that's the other way of looking at removing A. If we're not going to look at
excuse me.
Yeah. If we're not going to look at it mathematically, if we're just going to look at it from a more intuitive kind of basis, then we know that removing A, the reaction's going to want to make more A to replace the A that we removed. So then it will move to the reactant side.
All right.
Is that fair enough?
Yeah.
Does anybody have any questions about the Q and its relationship to K though? Okay, well, let's look at the next one, adding B. Now B, as you can see, is a reactant, and if we make B bigger, it's going to make Q smaller relative to K. That's why the reaction will shift towards the product side. Now, the other way of looking at that is to say, well, if we're adding more A, then the reaction's going to want to use, if we're adding more B, the reaction's going to want to use up that B that we're adding. And the way it uses up that B is by reacting with A and forming C. And that means that it's going to move to the product side if we add more B. Does anybody have any questions about this? Okay. Increasing pressure. All right, so the whole thing with pressure and volume in this part 3 here, and this is how you'll see it on the copy of the ungraded copy of test 1 as well. These only affect gas molecules, and I think that's really important here. And you'll see that when we get to these problems, that sometimes in those problems we don't have gas molecules. These are all gas molecules here, G, G, G. But if you had solid or aqueous, those remain unaffected when we're talking about gas molecules, because pressure and volume only affect gases and not solids or pure liquids or aqueous solutions. But the concept here is as follows. If we're increasing the pressure, what we've got to do is look at the number of gas molecules on each side. And here we've got 3 plus 2 is 5 versus 2 over here. If you're increasing pressure, then it's natural for the reaction to adjust in such a way that it compensates for the increase in pressure by going to the side that has the fewer gas molecules. So that would mean that it would go to the product side. Anybody have any questions about part 3 there? Okay, so the other way of looking at increasing pressure is the same as decreasing volume, because we have an inverse relationship between those two. Think of it like this piston here. If we're increasing the pressure by pushing downwards, actually let me put that arrow in a different location. We'll put it on the actual piston. There we go. And you can see that by pushing down on that piston, P goes up, but the volume goes down. I think that might be handy to have. Remember, you can have a sheet of paper in front of you for the test. I'd recommend having a little diagram like that just to remind you of the inverse relationship between pressure and volume. And that can remove a lot of confusion.
Will we ever have a question under constant pressure, or is that not?
Well, it's not relevant for part 3, Nathan. And that's because, we're actually making some sort of change here. Now, we'll say this. Let's say you had 2 molecules of gas on each side. Then changing the pressure or volume won't shift the reaction at all, because it's not really going to introduce any changes. So that's possible, but only if there's the same number of gas molecules on each side. All right, any other questions? The last one is somewhat confusing, or can be somewhat confusing, when we're talking about the heat here in the reaction. We're talking about this heat up here. Whoops, this heat here. This heat here is actually a product. I like to think of it as being a product, since it's on the product side of the reaction. The reaction is reacting A and B together, but it's producing C and heat. Heat is a product. So when I say I'm heating the reaction mixture, I'm not just heating one side. I'm heating the entire thing. And I think that's where people sort of get mixed up with that. They think, oh, the heat's only on one side, so I'm only heating up one side. No, you're heating the entire reaction. Now, it turns out that the way you can look at this is if you have C and you add heat to it, then what it's going to want to do is use that heat and form reactants. So think of the heat as being just like a regular product. If we're adding heat to it, then the heat is going to want to form more reactants. And that's how that works. Does anybody have any questions about number 4 there?
Would the inverse of that be true as well if you were adding heat, let's say, on the reactant side?
Yes, then what would happen? It would move towards the products if the heat was on the reactant side. And it could be, because then that's just a different kind of reaction. This is exothermic because heat's being created. Mm-hmm. But if heat was on the reactant side, then heat would be being used. It would be endothermic. Okay. But it still works the same way. Now, cooling means taking away heat. So that's a possibility as well. And that means removing, in this case, a product if it was cooling.
Because the heat is located on the product side in
that's right.
Equation. Okay.
That's right. You're taking heat away from it. It's like, think about just putting the reaction mixture in ice. That would be taking heat away. So it's going to want to create more heat to take into account the heat you've removed.
And it'll create more heat by working on the reactant side.
By reactants turning into products.
Right.
Yes, that's correct. Okay.
Mm-hmm.
All right. Does anybody have any other questions about this? All right, let's take a look at the test here, and we'll look at the questions related to that. Okay, and here we go. So number 12, calculate the value of Q. So for this one, let me erase what I've got over here. And the process I would use here, I'd go Q equals, and then I would go B squared C to the fourth over A cubed, and just plug those values in and then come out with the value for Q. Now, you're not asked to compare it to any K value here. So all you're being asked here is to calculate the value of Q, and you would do that just by plugging in those values. Does anybody have any questions? Any questions at all about that? All right.
So this one's structured a little bit differently in that there's one reactant and two products, but you still maintain the products over reactants, even if there's more than one.
Yeah.
I mean, it seems to be a little different than most of the samples that we've done so far.
But it could be, it could be anything there. It's always
right.
that way. In a more universal sense, it's always the product of the products over the product of the reactants, if that makes sense. And when I say product of products, I'm talking about all the products multiplied together by all of the reactants, and divide that by all the reactants multiplied together.
Okay.
All right, any other questions about that? Okay. Let's take a look at question 13. So it says here, a reaction A to B is found to have a Q value less than K. Which way will the reaction shift? So what I would do there is do up a little Q expression here, which is going to be B over A, products over reactants. And what it's saying is, well, the Q is less than K, and the reaction, and you want to know which way the reaction is going to shift if the Q is less than K. So let's make that, we'll make that K then, and we'll say the Q is less than K. And then the question you're asking is, well, what's going to have to happen? Well, B is going to have to get bigger and A is going to have to get smaller. So we're shifting towards the the products here to make more B. So I'd have to find an answer that went towards the products, and we know that B is going to have to go up and A is going to have to go down. And that means shifting it to the right. So it'd be the first answer there in this case.
All right, so like, what if the Q was greater than K? Would it have the opposite effect?
It would. You see, that's the thing. If Q was greater than K, then A would have to go up and B would have to go down. But those things happen simultaneously. If A is going up, it means that B must be going down because B must be turning into A. Does that make sense?
Absolutely.
Okay. Any other questions about this one?
Why wouldn't you reduce A as well?
You would. That's the thing. You mean in this question here specifically?
Yeah, I guess I guess whenever you say more, or is that the way that it's shifting? Does that make sense?
Well, all I can say is if you look at the answer here, it says B will go up and A will go down. This will happen as a matter of course. Because if B is going up, then A is turning into B, so A is automatically going down. In amount.
Okay. Yeah, it has to make it bigger.
That's right.
Okay.
And that's the thing. That's the way it's always going to be. You can't have. I'll say this: products and reactants can't both go up at the same time. That's absolutely impossible.
Okay.
Products.
Would that kind of go towards matter? Like it all has to be somewhere and it keeps shifting.
That's exactly right. Yeah.
Okay.
Yeah, because if A is turning into B, then A by definition must be going down.
Okay.
Is that fair enough?
Absolutely.
Okay. Does anybody else have any other questions about number 13? Now keep in mind I can have Q value greater than K as well for that. So just be aware that both possibilities there. Number 14, consider reaction below to be at equilibrium. In which way will the reaction shift if more C is added? So here I'm just looking for a direction. And if more C is being added, then what we're doing is increasing the amount of C on this side. And what will happen is that the C needs to get used up, which means it will go towards the reactant side. So it will shift towards the reactants. That would be the answer I'd put for that. Does anybody have any questions about number 14? And number 15. In what direction will reaction shift if A is removed? So A is going down, which means it wants to create more A to replace the A that we've removed. So it will shift towards the reactants again. Any questions? Okay. So question 16, we're looking at, it says here, what will happen with reaction pressure if the pressure is decreased? You need to count up number of gas molecules. So in this one here, we have all gas molecules, but sometimes we don't. That sometimes creates confusion. But if we had solid here, for example, you wouldn't count it. If you had aqueous here, you wouldn't count it. So I want you to be very mindful of these states here, because this whole pressure volume thing only applies when we're dealing with gas molecules and no other time. Any questions?
Only pressure, right?
Well, only when we're talking about pressure and volume. You know, increasing pressure, decreasing volume.
Mm-hmm.
Which specifically really only is for this question anyway, Adam, 16. So for this, go on.
For this, like, I feel like it won't shift because, it's the same amount of molecules on both sides.
You're exactly right. I hadn't gotten to that yet, but yes, that's right.
Sorry.
So since they have 4 and 3 is 7, 5 and 2 is 7, you're right, it won't shift. But what I'm saying here is Adam, if this was a solid, if this was solid here, then you wouldn't count the D as a gas molecule. It'd be 7 going to 5.
Right.
And that would be different.
So for that instance, if the pressure is decreasing, whenever we're thinking about pressure, are we thinking about the whole equation, or are we looking at reactants and products?
Well, I'd more prefer you look at it somewhat holistically and think of it just as being a piston. Mm-hmm. With the piston being pushed downwards, and asking yourself, well, what are the molecules going to do to account for that?
I mean, the volume's just going to decrease if there's more pressure coming down onto the piston.
Yes, there is that going to be that, and it'll go to a side that has fewer gas molecules in that instance. So think of it that way. You know, you've got to think of the whole reaction and what it's doing in order to compensate for that stress. Mm-hmm. In this case, it won't do anything because changing the pressure won't have an effect. Is that okay? Mm-hmm. Any other questions? All right, number 17 is asking, in which direction will the reaction shift if the reaction's heated? Well, think of the heat as being a reactant, and what will happen is it will shift towards the product side. And that's all I'm looking for. But again, we're adding heat, and we're going to say, well, what's going to have to happen? The heat's going to have to get used up. And the way it gets used up is by reacting with A and B to form more C and D. All right, does anybody have any questions? Okay. I'm going to get out of here.
Oh, actually, I was wondering if you can go over problem 18.
Problem 18. Let me see what that is.
It's the one with the variables in it, and you have to do like a little bit of algebra to it.
Oh, no, I'm doing that now. Give me a second.
Yeah.
All right. I'm going to go back to the, that's what I was going to do. I was going to go back to the test and show you the test question and then show you how that's done and then do that, okay? All right, so now we're going to look at question 4. And this is the one where we're dealing with the different things that are happening when we start off with a certain concentration of reactants, and then we have an equilibrium concentration of something. It could be a product or a reactant. And we're trying to determine what the value of K is based on that data. Now, the whole thing here, and for this, I'm not going to go through the whole thing here with the background because I really want you to go through that. I really just want to handle the actual mechanics of the problem today. But I would, I'd look at the mini lectures here, and what I would focus on is these last two here, Introduction to Calculating K and Calculating K. So these last two. If you haven't watched those videos, I would really encourage you to do so, because it gives you pretty important background as to why we're doing what we're doing and what this Z is and everything else that we're talking about. So for this problem, the way you'll set it up is by using what's called an ICE table, ICE, Initial Change Equilibrium. Generally though, if you look at the way I've set things up, I often don't even show the initial part here. I'll just show the change part, because that's really all that's well, I'll show the initial, I'll show the change, I should say. And I won't show any separate line that shows just a -4Z or the -2Z and a 3Z. All right, so let's talk about the signs first here, because those are going to be very important. If we're starting out with a certain amount of A and B, and we are here, we've got A equals 3.00 molar, B equals 3.00 molar. You can see that 0 is what C is. We know intuitively that the reaction can only go in one direction. And we know that the A and B have to go down and the C has to go up. So that first of all explains why we've got negatives there. So it's -4Z, -2Z, and +3Z on the other side. Does anybody have any questions so far? Well, let's talk about the Z's. The Z here is like a proportion. And if we look at I'll just play a little bit of the mini lecture here, just to show you the effect of what I'm talking about. Calculate the equilibrium constant K. Oh, what? I skipped to the next one somehow. Calculate the equilibrium constant K. So here's a typical problem that we're going to go down. What we've done is block 102. All right. So in this situation, you can see that we've got an initial amount, which is just going to be reactants, which in this case is SO2 and O2, with the SO2 being red dots and the O2 being blue dots. And then after a time, it reaches equilibrium. And you can see now we've got some SO3. What's important to note, though, is that there was no SO3 initially, and now there is. But in order to make that SO3, we had to use up SO2 and O2. So those concentrations went down. That's the first thing. The other thing is that they go up and down, the products and reactants go up and down, relative to the proportions that we use in the reaction itself. So we know that in order to make 2 SO3s, we use 2 SO2s and 1 O2. So the SO2s go down by the same amount as the SO3s go up, and the O2s go down by half of what the SO2s go down, because we only use one of those relative to 2 of those. That's kind of what I want to show here. Does anybody have any questions about that? Okay. So with that in mind, you can see that the way they go down is going to be -4 times an amount, which I'm calling Z. And the B goes down by half the amount because 4 A's and 2 B's make 3 C's. So that's going to be -2Z here. The thing in front of Z will always match the coefficient in the reaction. Anybody have any questions about that? And you'll see that the Z goes up 3Z. Again, it's 3C. So the most important thing is the sign, I think. I mean, handling the proportions is not that difficult, but just knowing that the reactants here need a negative and the products need a positive is going to be important. Any questions? Okay. The information that we're given here is that B at equilibrium is going to be 2.00. So we can actually calculate Z because we know that this is what's going to happen at equilibrium, 3.00 minus 2Z, and it has to equal 2.00. So we can do some algebra here to calculate Z, and Z comes out to here being 0.50. Does anybody have any questions about that?
Yeah, I actually have one question. So if B is given at equilibrium, so we have to figure out what A is at equilibrium too. Is that what we use? We have to find out what Z is, and then basically plug it in, and then that's going to be the equilibrium for each of those.
That's exactly right. Yeah. Yeah. And one thing that's annoying with this problem, though, is the significant figures. And, you know, what's going to amaze all of you here is that the calculation of Z here is actually an addition-subtraction problem. Wow. I just blew your minds, didn't I? I know you're looking at it saying 2Z. Well, that looks a lot like multiplication to me, Dr. Musgrave. The 2 there is a counting number. It's based on the reaction, and those are exact numbers. So it's not really 2 times Z, it's actually Z plus Z. So the answer for Z comes out to be 2 places past the decimal, which is why it's 0.50.
Okay, so we're given an equilibrium B molarity, and we only focus on the B only. So 3 minus 2Z equals 2.
That's right. That's to get the Z value, Adam. Yeah.
Okay. Thank you.
Now, once you've got the Z value, you can do exactly what you just said, and you plug that in. And this is how the student gets these values here, the 1.00 and the 1.50. They get that by plugging the Z value back in to the change that was listed here. And then we set up the K expression. I kind of wish the student had set this up, but I'll go ahead and write it out. But the K expression here would look like this. K equals C cubed, A to the 4th, B squared. And then all of those equilibrium values get plugged in at the end to get the K value. All right, does anybody have any questions about number 4? Any questions at all about what we're doing, why we're doing it? Yeah, does everybody understand it? Okay. Let's go back to the test here, and we'll look at that number 18 problem, Adam, you were asking about. Obviously, it's going to be different now. All right, so there's our reaction. 1A plus 1B gives 1C. And we'll go through and I'll show you how best to handle this. Okay. I want to do a couple of these, so I'm going to re-roll this in a second, you know, once we've done this problem. A plus B gives C. So initial is going to be 1.30 for A. And that's in molar. And we've got 2.50 for B. And you can assume that 0 is going to be C, right? We're assuming that all we have in solution initially is going to be A and B, which are the reactants. At equilibrium, A is 0.20. We're not going to use that yet, but we will in a second. So then we've got equilibrium. So what's going to happen at equilibrium? Well, it's just going to be 1.30 minus Z, 2.50 minus Z. These are just ones and ones, so it's just 1Z and 1Z. And then C is going to be just 1Z as well. So for this one, we know that A is going to be 0.20. So we also do 1.30 minus Z is equal to 0.20. And then we can solve for Z. And Z is going to be 1.10, right?
Yep.
Okay. So I like to go through and just do all these. I know what the concentration of A is at equilibrium. It's going to be 0.20 because that's what we were given. Now
Right.
B is going to be 2.50 minus Z, which is 2.50 minus 1.10, which is going to be 1.40. And C is going to be Z, which is going to be 1.10. So after that, we know that K is going to be C divided by A times B, and we can just plug all those values in, and that'll give you my K value. All right, any questions about that? Any questions at all? All right, I'm going to do, I'll do a couple more of these. To move this. Okay. Okay, so this one is 2A plus 1B gives 4C. Now, I can't remember this, but I think occasionally you might have possibly sometimes one reactant and two products. So, I mean, it can switch around as well. And you need to be prepared for that too, I think. All right, let's see. So we've got 2A, oops, 2A plus 1B gives 4C. And we're told that A is 1.20. This is initially 1.20, 2.60 on the B, and the C is 0. And then the change here, let me move this here. At equilibrium, then we're going to have 1.20 minus 2Z. We're going to have 2.60 minus Z, and then we're going to have 4Z over here. Now we're told here that A is 0.20, which means that 1.20 minus 2Z is equal to 0.20. So when I'm doing the math on this to figure out Z, that's going to be, Z is going to be 0.50. Any questions about this so far? I think I'm right on that, aren't I? Yeah. All right. Any questions? So let's look at A. A, we know, is going to be, well, we're told what it is. It's 0.20 to equilibrium. B is going to be 2.60 minus Z, which is 2.60 minus 0.50, which is 2.10. And C is going to be 4z, which is going to be 4 times 0.50, which is 2.00. And again, look at my significant figures there, because that's not a multiplication. It's actually z plus z plus z plus z, which is going to be 0.50 added to itself 4 times, which gives us 2 places past the decimal, which is 2.00. We plug that into the K equation, which I will squeeze in down here because I don't want to erase all this. So K is equal to c to the 4th over a squared and b, and we plug all those values in, and that'll give us the K value. Any questions about that?
You mentioned that sometimes the amount of reaction or reactants in products might have 1 on the reactant side and 2 products.
Mm-hmm.
Is it the K value where the change will really be different? I mean, everything else would be worked about the same.
Well, can I give you a for instance here, and
Yes.
hopefully it won't be confusing. Okay, I'm going to change this a little bit and change it up a little bit. I'll change it to 2A. Whoops. I'll change it to 2A gives 1B plus 2C. Right.
Okay.
Now in that instance, you wouldn't be given an amount for B then in the problem, Rebecca. You wouldn't.
Okay.
Because you're only ever given whatever it is on the reactant side. In this case, it's only A. So the problem then would become, I'll just do what the problem would be. The initial A is equal to 1.20, and at equilibrium, A is equal to 0.2. So that let's say we have that as our problem. So as I said, you will not get a B value then, because B is a product now in this equation. So when we do this, we have the initial, which is going to be 1.20, and this will be 0, and this will be 0, and then the equilibrium, this will be 1.20 minus 2z. This will be z, and this will be 2z. So you see the changes that would occur then? It's not just in the equilibrium itself, the K value.
Right.
Yeah, there's actual changes to the structure here as well.
Okay.
Now, the z value, again, is going to end up being 0.50 based on what we had done earlier. So then we could just continue with the problem at that point. But the K value is going to be B C squared over A squared. And you can see that B would be Z, which is 0.5 and 0.50, and C would be 2Z, which would be 1.00. And of course, A would be what we were told it was, which was 0.20. So then you would calculate it out from there.
Okay.
Is that fair enough?
Mm-hmm. That makes sense.
Okay. Does anybody have any other questions about K? So it's one of those problems. It looks really nasty when you first see it, but then when you really practice it and you beat it down, you beat it to a pulp, it's really not that bad. Right? You just have to practice it, and I think you'll be okay. How do you practice it? Just do this thing again and again. Just re-roll it, just like I just did now. And just do that problem again and again, and make sure you're getting the right answer every time, and then you'll be confident that you know what you're doing. All right, does anybody have any questions about 18? Any other question, 18? Adam, you were confused about it initially. How are you feeling about it now? Okay. Anybody have any other questions about 18? All right. So I'd like to leave the floor open now to talking about anything else. Now keep in mind, I did go through all the other questions in the previous Zoom session. Now, I'm not saying that those are off limits now, but I'm just saying that just for everybody's greater knowledge, that if you watch the previous Zoom session, you'll see that I will have gone through all those problems. I am more than willing, though, to go through examples of problems now, if people want to do that. So we can do anything off this test. So does anybody have any questions that they want me to go through here? Anything that's kind of a muddy point, something that you'd like me to talk about? All right, let me say one thing about this. I did send out an email earlier today just reminding people exactly what the story was going to be with this test. You can do the ungraded copy as many times as you like. You get 2 attempts at test 1. And that's going to be under honor lock. And the reason it's under honor lock is so that I know the person taking the test is the person doing the test and who's logged in. So that's why I've got the whole ID thing there. And then, you know, I'm hoping that again, I've allowing you to use a sheet of paper, handwritten notes, both sides. And that's how you'll do the test. It's due Thursday. Yeah, Rebecca.
Will we be able to have anything other than the one sheet of paper? Like, can we have blank paper if we show you the paper?
Oh,
just
sure.
To write?
Yeah, yes, yeah.
Okay.
Blank paper's fine. Yeah.
Okay.
It's not a problem. You'll need some. I can't imagine anybody not using the blank paper.
I need it.
Yeah, you can't do all this stuff in your head.
No. Okay.
All right. Any other questions? If nobody has any questions, I'll make up some questions. I'll do my own thing here, just for my own fun, and then you can follow along. But if anybody has anything specific that they'd like me to go through, I'm more than happy to do that. Well, either you all have no problems and you're all raring to go and get this done, or I'm hoping this isn't the case, that it's just so overwhelming you don't even know what to ask. I'm hoping that's not the case. All right, well, what I'm going to focus on is the last question, because that's the one that tends to annoy people the most, I think. Does anybody have any questions that they want to ask? Because that's what I'm going to do. I'm going to go through the last one.
Yeah, please do 22.
All right. Let's do it. So let's see what we have to do with this one first. So we've got, based on the following data, what would be the reasonable reaction set? We're given an overall reaction, and we're also given a rate equation here. Now, the first thing I want to do is ask myself this question, and that is the slow step the first step or the second step? Now, the way I tell that is I look at the rate equation and I see I've got A3B. And I look at A3B and I say, well, A3B, that's not a reactant. If A3B isn't a reactant, then it must have been made by something in the reactants, which means that the slow step must be the second step. So that's what I would do first. I would put that down as the second step. So to go A3B, the other thing I know is that the rate is always determined by what's going on in the slow step, which means that the only thing involved in the slow step is A3B. Now I'll leave a space below. I may or may not need a step below this. I know that I'm going to need a step here. I may or may not need a step here. We'll see. But I do know that everything has to add up to, the reaction.
So what's like the concept of what you're trying to do? You're trying to isolate the slowest step of the reaction?
Well, I already know what the slow step is because it's going to be determined by the rate equation every single time. Am I isolating it? No, I'm not so much isolating it. I'm just trying to determine it. At the present time, that's all I know is that A3B forms something and that's a slow step. That's all I know. I also know the slow step's the second step. not the first step. Is that fair enough? Why?
The second step is the slow step. How?
Because you see how this is A3B and that A3B is not a reactant here?
Right.
So the logic goes like this. If A3B isn't a reactant, it had to come from somewhere. I'll say that again. If A3B isn't a reactant, it had to come from somewhere. Where did it come from? Well, it came from these reactants, which means it had to be formed in a previous step.
Got it.
You see what I'm saying? I mean,
Yeah.
that's. I mean, I can say those words, but they really have to sink in, Wyatt.
They do sink in, yeah, because that other A from the reactants made A3B, so you'd have like A3B and C, and that would, right?
Yeah. Well, now that's the next thing we have to do, Wyatt. We have to say, well, if the A3B got formed, how did it get formed? Well, let's look at that. I mean, yeah, that's what we have to do. We know the A3B got formed in a previous step. So how did it get formed? Well, it got formed from, well, I can't just make A3B from A2B. I need both of those things. So both of these reactants would be required to make A3B. But then that wouldn't be balanced. So if I do that, it's going to be A3B plus C, and that's going to be a fast step. All right, I'm going to stop there for a second. Does everybody see what I did with that? Does anybody have any questions? Okay. In the slow step, what I want to try and do is make at least one of these products if I possibly can. But it looks like I might be able to make two of them. I could make AB and A2 out of that. AB plus A2, so I can account for both of those. I've already accounted for C as well. And what do you know? I've got the whole thing done. I don't need this. I don't need this step at all. So I would look for that specific reaction set in the list that's below, and then I'd hopefully find it. Does anybody have any questions?
When we're looking for the reaction set, it does need to be in that order. The fast step on top, the slow step second for this equation.
Absolutely, yeah. And if they're both labeled slow, that would be wrong as well. Or if you labeled the top one slow and the bottom one fast, that would be wrong too.
Okay.
Because the slow step has to be based on what's in the rate equation. And we also have to make determinations about where the slow step is, whether the stuff in that slow step had to be made from something else. Okay, any questions? Any other questions about number 22? I'm going to re-roll this. I'm going to re-roll. See what else we can come up with. Okay. Oh, I like this one because it's a little bit different to the one we just did. So why this will be a good contrasting one to this. Whoops. This will be a good contrasting one to what we just looked at. Okay, so we've got our rate equation here. It's AC. Now, what I want you to see here is, well, this is AC. AC is a reactant, so we know that the slow step must be the first step because it doesn't have to be made from anything. So, Wyatt, I'm going to ask you that question. Do you see that? Do you see that the slow step would be the first step in this case and not the second?
Right. So there's no reason to have a previous step here because AC is already in the reactants. Is your point?
I love to hear you say that. That's beautiful, Wyatt. That is beautiful. It's a beautiful thing. I love to hear you say that. That's great. Okay. So we know that the first step here is going to be AC gives something, and that's going to be slow. we also know that everything is going to have to add up to what we're given here. A to B plus AC gives AB plus C plus A2. So we'll try and make one of these. Now, the only thing I can make out of AC is just going to be C. But if I balance it, then it's going to be C plus A. Now I know I'm going to have a fast step here, and this fast step is going to involve, well, it's going to have to involve I've already accounted for the C here, but the A here is going to have to come down here. And what I haven't used yet is this A to B business. And that would allow me to make these last two products, which are going to be AB plus A2, which would be fast. And that'll be it. Any questions? So one question. Oh, sorry, go on, Rebecca. Go on.
I do have a question.
Mm-hmm.
Did you have to use the A out of the slow step on the product side in the fast step?
I absolutely had to, and I'll tell you why I had to do that. It's because A is not a product in the reaction we're given.
Okay.
So the inference there is that it must have been used up in another step.
Okay, and I think too, just skipping over what's going on in my head, I think that it's the difference between 2A versus A with a subscript of a 2. The difference in the molecules.
Yeah, so A2 would be a molecule where A and A are joined together. 2A would be two separate A molecules not joined together.
Right.
That's an important distinction, I think.
Yeah, I was thinking you could just break the A to B down into A, B, and A, and then that would give you your final product, but you can't because those two A's are different. And getting the A squared. Does that make sense?
Yeah, but you could possibly do that, but it would, I don't know if it's going to help you. It wouldn't, I don't think it would lead you to an answer that was easy. You'd probably end up getting maybe 4 or 5 steps out of something like that, Rebecca.
Because you'd end up with 2 individual A's and trying to get them together.
Yeah, that's right. But you'd probably end up just making them into something else, and they'd probably end up as A2s anyway. In the end, I guess it's the bottom line. You'd end up with 2 separate A's. You'd make them A2. That'd be another step, though. But but it'd be annoying. What you want to do is try and keep it as simple as possible. What you'd be suggesting would be more complicated. And I think therefore you might not see that answer. You probably wouldn't see the answer actually in the list that I have below.
Okay.
I've tried to keep it as simple as possible for those lists.
Okay.
All right. Does anybody have any other questions about that one? Does anybody? I'll do another example. I don't want to be annoying people if everybody understands this. Do you want me to? If anybody wants me to do another example, I'm more than happy to do so.
I'd like to see possibly a reaction order question.
Okay.
Or you can go with another one.
Well, okay. Let's see. Does anybody want any more question 22s? Because then we'll just go on to what Nathan's asking about.
No.
Okay. Nathan, which one? Give me a question number specifically.
I didn't have a specific question. Just something covering reaction order.
Reaction order. Okay. Hang on. Like maybe this one here. Find the order with respect to A.
Yeah, that'd be perfect.
Okay. Now, I want to point out that I do have videos for each of these questions in the folder below. There are videos for every single one of these questions of an example, so you can access those as well. Have you seen those, Nathan?
I haven't quite gotten around to looking at the question.
Well, let me show you where those are, but I'll come back to this in a second, I promise. So underneath here, you've got this practice test 1 videos, and these are the links to see questions 1 through 22. So if you have specifics about, specific questions about the mechanics of doing those problems, that's where you can go. But it doesn't give very much, these don't give very much background to the problems. The background is given in these mini lectures up here. That's where you're going to find the background, the why. I guess this is more like the how. But the why is as important as the how, in my opinion. Okay, so let's go back to where I was. Is that okay, Nathan? Do you see what I'm talking about?
Yeah. And I have checked out the mini lecture for that. I'm just mixing up the numbers themselves when I do the problem.
Okay, it's cool. That's cool. Yeah, I just wanted to make sure everybody understood that and saw it there. Okay, so we'll look at question 1 here. You don't have to actually do all this work, obviously, that I'm going to do here, but I'm just going to give you a little bit more context to just how I might do it if I was doing it in my head. We know that the rate equation is going to look like this. Rate equals K, A to be M, B to be N. And that if we're looking for A, we're going to have to compare 2 of the reactions where B is the same. So we'd have to use reactions 1 and 2. And I would do rate 2 over rate 1 because rate 2 is bigger. Now, as I said, in reactions 1 and 2, B are the same, so those are going to end up cancelling. The K's will end up cancelling. The rates are going to look like this. It's going to be 345 molar per hour over 164 molar per hour. And that would be, let's see, A2 is 0.346. And that's to the power of M, and that's over 0.168. And that's to the power of N. So I did the math there, and I've got my calculator here today, so I'm going to do that quickly. So we get to that point. You with me so far, Nathan?
Yeah.
Okay, so we can use this relation here to solve for z, where z equals log x over log y. And that will allow us to solve for m. So m would equal log of 2.10 over log of 2.05. And that's going to be 1, or it's going to come out to be 1. So we need to find what the nearest whole number is to that nearest integer. It's going to be 1. Any questions? All right. Does anybody have any questions about that one? Okay.
So I actually do have one question. So why is it 2.1 over the 2.5 instead of the other way around, perhaps?
Because, well, I'll do the, hang on, I'll do the thing here. I'm going to, I don't want to erase all that. I want to leave it there for a second. So I'll do it over here. But if you've got something like x equals y to the z, and you take the log of both sides, you'll have log x equals log y to the power of z. Now, by a log rule, we know that log x equals z log y. And so to isolate z would be log x over log y.
Thank you.
And again, since you have a sheet of paper in front of you, it's nothing to stop you writing that down, Nathan. So you don't get confused about which one.
Yeah, I think I might.
Yeah, it's a good idea. Does anybody have any other questions about that? Okay. Other requests? Other requests?
Actually, so I see where you did the 345 over the 164 got you 2.1. So with the M and the N, we simplified it, but we got rid of the.
Sorry, that should be an M. Sorry about that.
Oh, they're both M's. Okay.
Yeah. Sorry about that. I had meant to copy that down from up here, but I accidentally didn't write the full M in there.
Got it. Okay.
But you know the relation that we're using there is if you've got A to the M over B to the M, that's the same as A over B to the power of M.
Right.
Right?
Mm-hmm.
That's the relation we're using to do that. Okay, any other questions? Any other questions? All right. Anything else any questions anybody wants to go over on the test?
Can you just scroll through this copy?
Yeah.
To refresh me.
Okay.
Just so I can see where I have questions, because I do have questions as I go through the lectures and I go through the practice work, but then when I come here and we're going a different direction, it's a little confusing. I just want to see the questions. They're not. One thing I ran into with some of the practice work was you were asking the value of K nearest to
yes.
a list of numbers. It seemed like you wanted a number that was below the value of K, not over it.
No, whatever's closest. And often what I've done is I've allowed the possibility of more than one answer for that, Rebecca. So you'll see that when you go look at the submission, because it'll show you arrows next to multiple answers. And that's because I wanted people to be able to get an answer, but if it's close, just be able to have that.
Okay, but I don't see that on the test here.
No, it isn't. No,
it's structured differently.
No, that's right. That's right. But structured predictably, Rebecca.
That's right.
You know what you're going to get, right?
Right. Go through the test over and over.
That's right. That's right. Anyway, there you go. That's the whole thing. All right. Does anybody have anything that they want to talk about? All right. Well, if nobody, sorry, Rebecca.
I have one quick math question. I hope it's quick. It is back to the log.
Okay.
Can you explain quickly, because when we're doing the one with the half-life and the reaction orders, and we use a different key, and I just don't understand the difference mathematically
between
on the calculator.
ln and log.
That's right.
Right. Well, you've got two different buttons. They're often next to each other, log and ln.
Yes.
But specifically for now, here's the thing. For what we just did, there's nothing to stop you doing ln for both of those. You can do log and log, you can do ln and ln. You can't do ln and log, but you can do ln and ln. That'll work as well. That won't matter.
Okay. I have noticed that, but I didn't understand what the difference was between the two keys.
The difference is this. If you've got 10 to the x, that's a base 10. If you've got e to the x, and e is 2.38 something, it's a constant, then that's log to base e. That's the natural log right there. That's ln. And the 10 here, that's log.
Okay, would this be the same as the exponent key where you have like an x squared, which is like a standard, but then you have a y to the x where you're putting a different type of power in?
Well,
maybe even have a different base. Like
kind of. It's kind of like that. But this is really where it all comes from. It just stems from 10 to the x versus e to the x.
Okay.
And the reason it's called the natural log is because there's a lot of things in nature that abide by that constant.
The constant of 10?
No, the constant of e 2.3 something blah blah blah. It relates back to the Fibonacci numbers and
okay.
good golden rectangle and that kind of thing. A whole lot of different things. Okay. All right. Any other questions that anybody wants to ask about anything on this test? It's your time, folks. All right. Well, I guess we'll just leave it here for today then. If anybody has any specific things that they want help with, let me know and email me. And don't forget to take that test. You don't have to take it on Thursday. You can take it sometime before Thursday if you want. Take it today. Some people have already taken it, and that's fine. But you're welcome to do it any time up until Thursday, not past Thursday. All right. We'll leave it there then. And I'll talk to you all. I'll talk to you all soon. Thanks for coming.
Thank you.
Appreciate it.
Thank you. Have a good one.
You too. Bye-bye.